Alright guys, hi, this is Noah Jacobson, and we are going to be going over the 2007 FRQ number 4, which is shown here. So a particle moves along the x-axis with a position at time t given by x of t equals e to the negative t sine t on the interval between 0 and 2 pi. Alright, so for part A, they're saying find the time t where the particle is farthest to the left. Justify your answer. So when I first saw this problem, I was a bit confused about the left part of this. I'm unsure how they define left. But you see in the problem they say the particle is moving along the x-axis. So here's our theoretical x-axis, right? As you go this way, you get more positive, and you also get more to the right. And as you go this way, you get more negative, and you are going to the left. So what they're basically asking in this problem is, what is the absolute minimum of the function e to the negative t sine t? Here, let me just write that out there. So they want to find minimum of that on the interval from 0 to 2 pi. Okay, so as we know, to find the minimum of a function, we want to find when the derivative equals 0 to get some critical numbers. So the derivative of x of t, to find that we're going to want to do the u prime v plus u v prime strategy. So we take this derivative times this normal and add it to this normal times this derivative. So that ends up coming out to be e to the negative t cos t minus e to the negative t sine t, which we can also write as e to the negative t times cos t minus sine t, which is terrific. Alright, so now we want to find that equal to 0. So setting equal to 0, we got that. So e to the negative t, that's never going to equal 0 because it's an exponential. So we can just divide that on both sides and ignore it. Then as far as this goes, we can kind of add to the other side. So basically we know when sine t equals cos t, there's going to be a critical number. Alright, so at what points are these equal to each other? Well, we know from trig it's going to be pi over 4 or 5 pi over 4. So those are our critical numbers. We also, a refresher, we also need to consider the endpoints too when we're finding an absolute maximum or minimum. So we take our points now that we're going to test. 0 pi over 4, 5 pi over 4, and 2 pi. Probably draw lines in between these, just so you don't get confused. And we're now going to find what the value of x of t would be at these intervals. So here we have e to the 0, sine of 0, which, because sine of 0 equals 0, equals 0. I'm just going to jump ahead. We have a similar thing down here with 2 pi, e to the negative 2 pi, and sine of 2 pi. Because sine of 2 pi equals 0, let me move this up. Because sine of 2 pi equals 0, this whole thing is going to equal 0. Alright, now getting out to these ones, I'm going to do this 5 pi over 4 first. So e to the negative 5 pi over 4 times the sine of 5 pi over 4 is going to equal some negative number, because as we know, if you're drawing your coordinate plane and you get to 5 pi over 4, this sine value is going to be negative. Okay? So I'm just going to write neg. Then for pi over 4, conveniently enough, e to the pi over 4 times sine of pi over 4 is actually a positive value. So since we're trying to find the minimum, remember, of this function, we can decide now that the absolute minimum is going to be 5 pi over 4. So when the function is farthest, when the particle is farthest to the left, the time is going to equal 5 pi over 4. Alright, so that's part A. And now we get to the seemingly more complex part, part B. Alright, I'm going to move this phone down a bit just so we can get the bottom half of this page. Alright, find the value for the constant A which satisfies the equation A of the second derivative of t plus the derivative of t plus x of t equals 0 on the interval from 0 to 2 pi. Alright, so I'm just going to write that again here, just for reference purposes. So now the next step would be to find x of t, x prime of t, and x double prime of t. So we know x of t is going to equal e to the negative t sine t. We know x prime of t from the last problem is going to equal, and I'm just going to write it out in its kind of longer format, e to the negative t cos t minus e to the negative t sine t. And then x double prime of t is a bit harder to solve. You would want to take e to the negative t times cos t minus sine t, and again use the product rule. And to save some time, I already found that. So we know the second derivative is going to be negative 2 e to the negative t times the cosine of t. And that just simplifies that because sine and cosine end up canceling each other out with the product rule kind of stuff. Alright, so now plugging that back into this equation, we know negative 2a e to the negative t cos t plus e to the negative t cos t minus e to the negative t sine t plus x of t, which is e to the negative t sine t, equals 0. So we want to solve for a there. So we know this stuff cancels out. Don't really need to be concerned about that. Then as far as this goes, we can just swap the sides of one of the things. So negative 2a e to the negative t cos t equals negative e to the negative t cos t. Then we can divide some stuff, cancel this stuff out, and so that it end up being 1. We divide both sides by, or negative 1, we divide both sides by negative 2, and we get a is equal to 1/2. Before I go, I just wanted to give a brief explanation of the extreme value theorem. So the extreme value theorem states that on a closed interval from a to b, there is going to be an absolute maximum and an absolute minimum on the interval. So as you can see here, our absolute maximum would probably be about here, and our minimum would probably be about here. Alright, if you need more help on learning about the extreme value theorem, there are problems in our book on the applications of derivatives chapter. If you go to the previous chapter on derivatives itself, you'll be able to learn more about taking derivatives, more about the product rule, and all that. Thank you guys so much for watching. Specifically, on page 278, I like problem number 70 because it shows a practical application of this in physics. Also, on page 188, problem number 44 is great for getting a good understanding of the product rule.